In this lesson, we learn about addition, subtraction, multiplication, division, and composition of functions. We will cover average rate of change and difference quotients. Then we learn to find inverse functions. And then we learn to find specific terms of arithmetic and geometric sequences and find explicit formulas for arithmetic and geometric sequences. Functions are mathematical objects like numbers, and we perform operations over functions. For instance, let f of x equal x squared minus 3 and g of x equal square root of x plus 1, then minus 2. Then the sum of these two functions f plus g of x is simply f of x plus g of x. We put these two functions together and combine like terms to add them. In this case, we can only add negative 3 and negative 2 and get x squared minus 5 plus square root of x plus 1. F of x has no domain restrictions and has a domain of all real numbers. However, g of x has domain restrictions where the square root can only be defined for non-negative numbers and has a domain of negative 1 to infinity, including negative 1. And since the sum f plus g includes both functions, its domain must satisfy both functions. Therefore, domain of f plus g is negative 1 to infinity, including negative 1. The difference of f and g is similar to the sum, where we simply subtract g of x from f of x. We put the two functions together to perform the subtraction. We first distribute the negative into g of x, and then combine the like terms. We already know the domain of f of x and g of x. And since the difference involves both functions, its domain must satisfy both functions. Thus, it is negative 1 to infinity, including negative 1. The product of f and g is simply f of x times g of x. We put these two functions together to multiply. We need to FOIL them. So, x squared times square root of x plus 1 is x squared times square root of x plus 1. X squared times negative 2 is negative 2x squared. Negative 3 times square root of x plus 1 is negative 3 times square root of x plus 1, and negative 3 times negative 2 is positive 6. Unfortunately, none of these terms are like terms, and this cannot be simplified further. Domain of fg is also negative 1 to infinity, including negative 1, as it must satisfy both f and g. The quotient of f and g is f of x divided by g of x. That is, x squared minus 3 divided by square root of x plus 1 minus 2. Domain of f over g must satisfy both of these functions. But we also have a denominator where it cannot be 0. So we set square root of x plus 1 minus 2 not equal to 0 to find the values of x that make the denominator 0. We add 2 to both sides and get square root of x plus 1 not equal to 2. We can see that when x equals 3, square root of x plus 1 equals 2, so x cannot be 3. Negative 1 to infinity satisfies both f and g, and we need to remove 3 as it makes the denominator 0. So removing 3 from negative 1 to infinity, we get a domain of negative 1 to 3, including negative 1, union 3 to infinity. The composition operation is another mathematical operation where the output of one function becomes the input of the other function. F composed onto g of x by definition means f of g of x. F takes its input and squares it and then subtracts a 3 from it. And the input of f is g of x in here. So we simply take g of x and square it and then subtract a 3 from it. To square square root of x plus 1 minus 2, we need to write it twice and FOIL it. We're going to skip this process as we have done it previously. So we get x plus 2 minus 4 times square root of x plus 1. And the domain of the composition is negative 1 to infinity, including negative 1. Difference quotient is the measurement of average rate of change over an interval. Here's a function f of x. Let the interval be from a to b. Then the average rate of change is f of b minus f of a, all divided by b minus a. Note that This is just like the slope formula. The difference quotient can be measured about a point. Let the point be C and the interval be C minus h to C plus h. That is the interval with h units away from C in each direction. Then the formula f of C plus h minus f of C all divided by h can be used to calculate the difference quotient. Note that as the value of h decreases, the difference quotient more accurately represents the rate of change at point C. And when h becomes 0, the green line becomes the tangent line. Here's an example where we're asked to find the average rate of change for f of x between 3 and 5. So the average rate of change is f of 5 minus f of 3 all divided by 5 minus 3. On the side, we find f of 5, where we simply input 5 for every x in f of x and simplify it to 65. And then we find f of 3, where we input 3 for every x in f of x and simplify it to 21. And then input these values into the formula of average rate of change and simplify it to get 22 for the average rate of change. Here's another example where we're asked to find the difference quotient of f of x. The difference quotient formula is f of x plus h minus f of x all divided by h. We first find f of x plus h by inputting x plus h for every x in the function. For x plus h squared, we need to FOIL it and then distribute the 3. Once we have f of x plus h, we put it in the formula. Distribute the negative into f of x and combine the like term to get 6xh plus 3h squared over h. We can simplify this by factoring out an h and canceling the h's. So the difference quotient is 6x plus 3h. Inverse functions are extremely important as they map the output of a function to its input. A function f of x has an inverse function f inverse of x if it is 1 to 1. And the domain of the function is equal to the range of the inverse function, and the range of the function is equal to the domain of the inverse function. Two functions f and g are inverses of each other if they are both 1 to 1 and their composition f of g of x and g of f of x are both equal to x. To find an inverse function of f of x, we can follow a series of steps. First, we need to make sure f of x is 1 to 1. Otherwise, it does not have an inverse function. If f of x is 1 to 1, we proceed to the next step. The second step is to replace f of x with y. Then we switch x and y, solve for y, and then replace y with f inverse of x. And finally, we check the domain restrictions to ensure the domain of the inverse function equals the range of the original function. Here's an example where we are asked to find the inverse function for f of x. First, we check to see if f of x is 1 to 1. Any rational function of the form linear over linear or constant over linear is 1 to 1. Therefore, f of x is 1 to 1. Then we replace f of x with y, switch x and y, and start solving for y by multiplying both sides by y plus 3 and distributing x into y plus 3. To solve for y, we want all occurrences of y to be on the same side. So we subtract y and subtract 3x. Then we factor out y and divide by x minus 1 to solve for y. And last, we replace y with the inverse notation f inverse of x. In this example, the domain of f inverse of x is equal to the range of the original function f of x. Here's another example where we are asked to find the inverse function for f of x. We know that the graph of f of x is a parabola opening upward. This graph does not pass the horizontal line test, and so the function is not 1 to 1, and therefore there is no inverse function. Here's another example, but this time the parabola is limited to only non-negative x values. So f of x is 1 to 1, and therefore it does have an inverse function. We replace f of x with y, switch x and y, and try to solve for y by simply adding a 3 and then taking the square root of both sides. Note that since we took square root of both sides, we give one side plus or minus. However, with the plus or minus, y would not be a function of x. We know that the range of an inverse function should equal the domain of an original function. Thus, the range should be real numbers greater than or equal to 0, same as the domain of f of x. So we only take the positive square root of x plus 3 in this case. So f inverse of x equals square root of x plus 3. A sequence is a discrete function where its domain is the set of whole numbers. A sequence is represented with an explicit formula a sub n, where a sub n is the nth term of the sequence. Here are some examples of sequences. The first set is a sequence with the first term of -3, while the rest of the terms of the sequence are 2 more than the previous term. The second set is a sequence with the first term of -2, while the rest of the terms are -2 times the previous term. And the third set is a sequence of powers of 3 with the first term of 3. An arithmetic sequence is a sequence that has a common difference d between the terms and behaves like a linear function. We use the formula a sub n equals d times n minus m plus a sub m to find the explicit formula for an arithmetic sequence, where a sub n is the nth term of the sequence, a sub m is the mth term of the sequence, and d is the common difference. Note that the formula of the arithmetic sequence is very similar to the point-slope formula of a line, where a sub n is like y, a sub m is like y1, slope is like d, n is like x, and m is like x1. If we add a sub m to both sides, we get the formula for the arithmetic sequence. Here's an example where we're given an explicit formula and are asked to find the first 4 terms of the sequence. The first term, a sub 1, is when n is equal to 1, that is 1. The second term is when n is equal to 2, that is 4. The third term is 7, and the fourth term of the sequence, a sub 4, is 10. Here we're asked to find the next 3 terms of the sequence. We can see that -2 minus 3 is -5, -5 minus 3 is -8, and -8 minus 3 is -11. So it seems like the common difference is -3. In that case, we subtract each term by 3 to get to the next term. That is, the next 3 terms are -14, -17, and -20. Here's an example where we're asked to find the explicit formula for an arithmetic sequence whose 7th term is 20 and 15th term is 32. We know the formula for the arithmetic sequence. Let a sub n be the 7th term where n is 7, and a sub m be the 15th term where m is 15. Substituting these values into the formula, we get 20 equals d times 7 minus 15, then plus 32. In solving for the common difference, we get d equal to 3/2. Now that we have d, we can use d and values of m and a sub m to write the explicit formula. We get a sub n equal 3/2 times n minus 15, then plus 32. We can distribute 3/2 into n minus 15 and simplify to a sub n equal to 3/2 n plus 19/2. A geometric sequence is a sequence that has a common ratio r between the terms and behaves like an exponential function. We use the formula a sub n equal to a sub m times r to the n minus m to find the explicit formula for a geometric sequence, where a sub n is the nth term of the sequence, a sub m is the mth term of the sequence, and r is the common ratio. Here's an example of a geometric sequence where we're asked to find the first 3 terms of the sequence. To find the first term, we simply input 1 for n and simplify it to get 6. For the second term, we input 2 for n and simplify it to get 3. And for the third term, we input 3 for n and simplify it to get 3/2. In this example, we're asked to find the next 3 terms of the sequence. We can see that -2 times -2/3 is 4/3. 4/3 times -2/3 is -8/9, and -8/9 times -2/3 is 16/27. So this looks like a geometric sequence with a common ratio of negative 2/3. In that case, we simply multiply each term by negative 2/3 to get to the next term. Hence, the next three terms are negative 32/81, 64/243, and negative 128/729. In this example, we're given the 7th and the 10th term of a geometric sequence, and we're asked to find the explicit formula for it. We know the formula for the geometric sequence. Let a sub n be the 7th term where n is 7, and a sub m be the 10th term where n is 10. Then we get 8 equal to 216/125 times r to the 7 minus 10. We can multiply both sides by 125/216 and get 125/27 equal to r to the negative third power. That is, r cubed equals 27/125. And by taking the cube root of both sides, we can solve for r and get r equals 3/5. Now that we have r, we can write the explicit formula for the geometric sequence as a sub n equal to 216/125 times the common ratio 3/5 to the n minus 10, which can be simplified to a sub n equal to 8 times 3/5 to the n minus 7 power.